Hello, everyone. How are we doing today? Doing all right? Okay. Um, there's a issue that I want to make sure that we talk about more completely before we move on to the new material here, and that has to do with the idea of the form of fundamental subspaces. So, in the online notes, there is a wonderful couple of videos covering this topic. By Gilbert Strang. I don't know if you all heard about this. Maybe somebody in one of your other classes mentioned it. He was a very famous lecturer who was at MIT for years and years and years. Uh, the thing that he was the most well known for was his presentation of linear algebra um, at their university. And it was to the point to where when he retired and gave his final lecture, like standing ovation, big deal on campus, all of that stuff. Um, um, OpenCourseWare for MIT has existed for quite some time. They were one of the leaders in providing educational resources online for um, anyone to take advantage of. All right, and obviously Gilbert Strang's material is on their website and stuff, and there are several videos that are featured in our online notes. So I recommend that you take a look at that. Um, there are some things about the way that I teach the class that are inspired by Mr. Strang, and you should. There are things that he does in a way that I can't quite replicate. Um, so please do check those out. But I want to make sure that we go back and cover cover these ideas so that we know what's going on. All right. So we've talked about column and row space. Okay. So if I have a matrix A and that matrix is an M by N matrix, we want to understand what's going on with this matrix. So we think about A as being an object that has N columns here and M rows. Okay. So if we talk about the column space of A, the column space is the span of the columns of A. I'm going to write this in a very weird way, but this is the standard notation for it. Now, rather than trying to be too cute about the notation we use, the easiest way to understand this is we're just talking about the span of the rows of A. So what that means is I'm thinking about taking the rows of A, turning them into column vectors, and then talking about that span. Okay? We have these two ideas together, all right? Now, because we're talking about spans, we know that we're talking about subspaces because that's one of the elements of the discussions that we've had, right? Okay. If we have a span of vectors, then that span forms a subspace. Okay. Now, connected to these two ideas, we have a different set of values. Okay. Okay. So the two that we've talked about are the column space and the row space. Here we have the set of all vectors in Rn such that A maps x to 0. Okay. We've talked about this before. This is the null space of our matrix. All right. And then can you all guess what the last one's going to be? Now, when we've previously talked about subspaces of vector spaces, we have indicated that the zero subspace and the entire subspace, that is the space that's equal to the vector space, are trivial. Okay? Would it make sense to talk about all of A or all of vector space associated with A if we're referring to fundamental subspaces necessarily? Or would there be something else maybe that we would want to talk about? Now, I was interested in the column space of A and the column space of A transpose. Talk about the null space of A. Sorry? Rank is involved, but not yet. Okay, I was about to say that I thought that I may have misled you, but somebody got it. It's the null space of A transpose. So this is, sorry, I forgot to underline this X. That X should be underlined. Okay, so this is the set of all vectors in Rm, because we're talking about A transpose, that get mapped to 0. So, thing to note, obviously this notation is written to mean the column space of A transpose, but we call it the row space. All right, to make the notation hopefully not confusing. Now, there are some places that use awful, 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 awful notation for this. And they'll use R of A, but mean the column space. Grinds my gears. I hate it. All right, so be on the lookout for that. I'll try to be consistent and use notation that's not uh, just bad. But do know that that's out there in the world. All right. Okay. Now, when it comes to how we interpret what's going on here, uh, someone asked about the rank of a matrix. Okay. Now, the rank of a matrix is connected to what's going on with the column space and the row space of a matrix. Okay. Now, what did we say was the rank of a matrix? Okay. So we say that rank is the number of linearly independent columns of A. All right. Now, what's another way that we can characterize the rank of a matrix? I think you're both probably going to say the same thing. Go ahead. You, huh? Okay. When you say the ones with a non-zero number, what specifically do you mean? Okay. So the answer had to do with row echelon form. We know that there are going to be some matrices where if we put it into reduced row echelon form, that we're going to have some number of rows that have this property. Okay. The other way to think about it would be that there would be some number of pivot columns that exist in the form. Okay. Those That idea is correct. It's not stated in exactly the way that I was looking for, because I want to call back to what we're talking about. And what were you going to say? It's the dimension of actually either of these. Okay. One of the things that we'll find out is that the dimension of the column space is equal to the dimension of the row space. Okay. Or one of the things that turns out to be true. Okay. So an equivalent statement to saying that the rank is the number of linearly independent columns of a matrix is because the column space is the span of A, that is the span of those columns, that the dimension here has to equal the rank. Okay. So this is a big deal. All right. We have the dimension of the column space being equal to the rank of the matrix. This gives us a pretty important part of the picture that we're trying to understand here when it comes to what is it that a matrix does. Okay. So this gets tied very importantly to the mapping. All right. And beyond this, we have, pardon me, we want to continue on with this idea. Okay. I want to talk briefly about the idea of image of a mapping. Okay. In mathematics, all right, there is the idea of having some set, all right, and then I have some function f that will take the elements of this set and map it over here to some other spot, right? Okay. And the collection of all of the points in this, which we call the domain, and this, which we call the codomain, the part that actually gets mapped to is known as the image. Okay. Now, in your previous math classes, you probably have only ever heard the terms domain and range. All right. As time goes on, I think that the idea of range is probably going to fall out of style because mathematicians universally hate it, and they will work very hard until they finally get the textbooks rewritten. But the idea here, more or less, would be if we imagine that we're throwing darts at a dartboard, the codomain is the dartboard, and the image is the place where we actually impact with the darts when we throw them. Okay, that's the difference. All right. Now, unfortunately, range is kind of used to mean both things. All right, but we need to distinguish between these two ideas. Okay. Okay. So the idea here is that if x is a vector in Rn, okay, A is going to map that to some vector in Rm. Yes. We are thinking about our matrix A as a function. Okay. We will call these functions linear transformations. All right. We haven't quite gotten to the point where we're using the vocabulary yet, but that's what we're building up to. So good observation. So yes, we're thinking about A as a function that takes a vector and then maps it to another vector. Okay. We have an element in Rn that gets mapped to Rm. That's why it's an m by n matrix. And the matrix multiplication works like this. Interior dimensions match, exterior dimensions give us the product, or the dimensions of the product. Okay? So, if I think about the set of all possible vectors in Rn, the image of the mapping under A is the column space of the matrix. Okay? So here we have all of Rn, and here we have the subset or subspace of Rm that gets mapped to under the transformation of A when I apply it to any vector in Rn. Ideally, the image is equal to the codomain, but that doesn't always happen. And that is the purpose of our fundamental subspaces. Is there's going to be some things that aren't in the image of A, and those things are going to have to be part of the null space of A. They're the vectors that get mapped to 0 because they won't exist in the image, right? We've talked about how sometimes when we multiply a matrix times a vector, dimensions disappear. This is how we think about it in terms of the notion of vector spaces and subspaces. All right, so one of the things to make sure that you're aware of, okay, are the things that are connected to the rank of a matrix. All right, now I know people in here are younger than me. All right, that means number, not hashtag. Anyway, so these things are all the same. All right, the dimension of the row space and the column space are equal. All right, that means that the matrix should have the same number of pivot rows and pivot columns. Okay, all of these things are a way to measure the rank of a matrix. We say that a matrix is full rank if it has the same number of pivot if every column is a pivot column. This is the shortest way to say that. All right, now there's a very important theorem. We have an m by n matrix. Then the null space of that matrix is trivial if and only if I wrote it out. Yeah, yeah. The null space is trivial. That is, the null space is exactly the zero vector, if and only if A is full rank. Okay, so The phrase if and only if means that I should be able to do the if then in both directions. If A has a trivial null space, then A is full rank, and if A is full rank, then it has a trivial null space. So we'll do the implication this direction first. So let the null space of A be the zero vector. Then the only solution of the homogeneous system is x equals 0. Okay? All right? That means that if I write out a linear combination of values that equal 0, then what this implies is that I have the following system here. All right? I'm going to write this in a different color so it's clear. What I have is a linear combination of A's columns. The only way for me to get a linear combination of A's columns to be equal to the 0 vector is for C to be the 0 vector itself. I have proven that the columns are linearly independent. A is full rank. Make sense? So there's 3 parts to this. Null space is trivial, so the homogeneous solution only has x as a solution, right? I write out a linear combination of the columns of A. And I set it equal to 0 because that's the only way that something else could be in the null space, right? Okay. This linear combination is only equal to 0 if C is 0. That's the definition of linear independence. A matrix is full rank if all of its columns are linearly independent. Questions about that? Okay. Now, this proof going backwards is basically the same. We have A is full rank, so its columns are linearly independent. if we construct the linear system AX equals 0, the only possible solution is 0 because the columns of A are linearly independent, right? So we get that the null space is trivial. Okay, those it doesn't always happen this way, but those steps are basically all reversible, right? Okay. The reason we went through this is because it leads up to one of the most important ideas in linear algebra and the reason why we care about these fundamental subspaces. And that is the rank nullity theorem. I wrote them backwards, but sorry. The dimension of the null space of a matrix is known as its nullity. Okay? The nullity and the rank have to sum to be the number of columns of the matrix. I wrote this poorly. It's m by n. Okay? All right. Now, on the notes page, there is a bunch of consequences of the rank nullity theorem. Okay? Which says that if we have X and Rn, it's in both the null space and the row space, then we have that Ax equals 0 and X equals A transpose Y for some Y in Rm. All right. This gives us this expression, which tells us that we're going to have 0 here. All right. So the only vector that is going to be in both the row space and the null space of a matrix is the 0 vector. Okay, so they share their intersection is exactly 0. Okay, if we swap them, we see that the intersection between the column space and the null space of A transpose is also exactly 0. Okay, so there's a bunch of mutual orthogonality going on. All right, if we're thinking about the orthogonality of stuff, being related to their dot product. Okay. So one of the projects that you have to work on has to do with direct sums. Okay. The idea behind a direct sum is that we have orthogonal subspaces. All right. That is subspaces that only share the zero vector. Okay. Or should. And if you take a direct sum between those two subspaces, you should get the entire vector space. This is what can be done with these subspaces here. All right, you take the column space and the null space, or the row space and the null space of A transpose, okay? Or you can swap the column space and the row space, all right, in those relations, and you get the ability to create direct sums. Okay, so we can always factor, so to speak, our vector space into components that interact with our fundamental subspaces here. Okay, does that make sense? Okay, that's the connection between that assignment and kind of the broader picture of linear algebra. Okay, and there's also another video to check out, by the way, of another Strang video dealing with the big picture of linear algebra. Okay, so I think there's 2 or 3 videos on this page that you should check it out to cement these ideas. All right, let us continue. All right. Okay. So the next idea that we want to talk about is related. We've now gotten deeper into what matrices are representing and what's going on algebraically with sort of the deeper meaning of how these things interact. And what we want to do now is we want to talk about different ways that we use matrices in practice. Okay. In response to a question, I mentioned the idea of a linear transformation. This is what we're building up to. Okay. But there's some stuff that we want to make sure that we understand first. Okay. Okay. Recall that a basis is a linearly independent spanning set for a vector space. Okay. When we are working with objects in linear algebra, what we want to do is we want to have bases in order to be able to discuss things to make our lives easier. Okay. So, for instance, if we're talking about R2, we have the standard basis given as I've written here I hat and j hat. Okay. We of course know that this means this collection of vectors. Okay, given like so, and then also just so I don't forget to mention it. It is generally the convention to use E with a subscripted number as the notation for a standard basis in a general vector space. Okay? So E1 and E2 look like this. It's the only non-zero element in the vector is the one indicated by the subscript. Okay? Now, also in R2, we could have a different kind of basis. So we can have these two examples here. Now the question is whether or not this is a reasonable basis. We know that the way that we prove this is by showing that it's row equivalent to the identity, right? We need to determine if the columns are linearly independent. Okay, we can do this with a couple of row operations. I'm not going to worry about writing out specifically what we did here. I think it's easy enough to follow. Okay, but we can get that this is row equivalent to the identity. Columns are linearly independent. Every column is pivot column. All right, so this is a fine basis. Okay. Now, what this means is that each vector B that's an element of two-dimensional space may be written as a linear combination of these vectors. That is to say that B is equal to 1, 2, x1 plus 2, 1, x2. Okay? Okay. And so x1 and x2 are the coordinates of B with respect to the basis 1, 2, 2, 1. And then I've talked about this abbreviation before, right? Yeah, I think I have. I just want to make sure. Okay, so the idea here is that we can use this linear combination in order to represent the vector, okay? And what we want to do is set all that up, okay? Now let's do an example here. Okay. Say I have the vector 3, 3. And we think about this vector 3, 3 as being written in the standard basis. Okay? Now, that means that coordinates work the way that we're used to thinking about coordinates working. So if I call this vector v, what that means is that v can be written as a linear combination of my standard basis vectors. Okay? This is known as standard coordinates. What I would like to do is put it into non-standard coordinates, utilizing the basis that we talked about before. Okay, and just so I've said it, there isn't a reason that I'm, other than laziness, switching between parentheses and square brackets here. Just I didn't feel like drawing the square brackets earlier, but I'm going to be more careful about it now. All right. So we want to switch to the idea of figuring out what this looks like. Now, in order to do this, I want to figure out how to make this happen. Okay? I can either use these vectors to form a matrix A and then solve this linear system, or we can observe that V is going to be equal to 1 times 1, 2 plus 1 times 2, 1. Okay? Yeah, it's just this problem is so easy that you can look at it and tell the answer. All right, is all this means. The mathematicians refer to this as solving a problem by inspection. It just means the problem's fairly easy and you can look at it and guess what the answer is supposed to be. All right. Now, doing all of this, okay, it tells us that we can write V as 1, 1 with respect to the basis E, where that subscript indicates that we're in a non-standard basis. Okay? Now, bases are ordered. Okay? There's a big difference between writing this and this. All right? We follow order. We have to understand the ordering of our coordinates. So whenever you choose a basis, you're choosing not only the elements of that basis, but the order in which they are presented. Okay? If we're in 3D coordinates, x, y, z is a different coordinate system than x, y, or z, y, x. Okay? All right. Now, when we talk about coordinates, I'm going to write this in red because it's important. It only makes sense to talk about coordinates after we have chosen a basis. Okay? A vector is an object that exists mathematically independent of the coordinate system in which it is expressed. Okay? We tend to identify a vector with its representation in a coordinate system, and that representation is going to end up being unique. But because there are many, many, many valid choices of coordinate systems, that doesn't mean that a vector is tied to any particular one of them. Okay? The idea of a vector is separate from the coordinate system in which we choose to express it. All right? It's the same thing as we have an idea of what 2 is or what 3 is, all right? But that idea isn't tied to me writing this or this. This is a numeral that I use as a placeholder to represent the idea of 2 or 3, okay? But it doesn't mean what 2 or 3 does. Same kind of broad idea. I don't know. If we want to go back to Shakespeare, I guess the quote would be, "A rose by any other name smells as sweet." All right. The idea of what it is separate from how we represent it or call it. All right. How long is this video? Okay, it's short enough. All right. So, in lieu of me talking for another 20 minutes, I'll talk for however much time we have left. But this is gonna go. All right. I'll turn it down if I need to. But we're gonna watch the 3 blue 1 brown video about change of basis. All right, for context here, and then we'll pick up after the video's done. And I might pause once or twice if I feel like there's something I need to say. All right. So questions about what we just saw there? Yeah. So the We'll call this a general transformation. I might introduce more vocabulary for it later, but it's not really what we're interested in right now. Okay, so what we're talking about is something that looks like this. All right, we have some vector, and what we want to do is we have the vector, and there is a transformation that we understand here in terms of the standard basis. Okay, we've worked with the standard basis in more or less our whole lives. Okay, and it doesn't necessarily have to be in the standard basis, but it's in the context that we are aware of. So the standard basis is normally what we have here. And this is the new basis and the inverse of the new basis, those transformation matrices. Okay? And so the process that was being described at the end is if I want to get back to a vector that is represented in a non-standard basis under a transformation that is represented in the standard basis, we convert to the standard basis, apply the transformation, and then convert to the non-standard basis. So translate, transform, and return. All right. Now, I mentioned this a little bit beforehand when I was talking about vectors, and the video kind of hinted on it with hinted at it without saying it explicitly. But the idea of coordinates and coordinate systems and how we represent objects is tied up in that representation. Okay, the vectors themselves are just things that have magnitude and direction. Okay, it is up to us about how we decide how to measure that magnitude and how to express that notion of direction. Okay, those things are both in different ways tied up in our choice of coordinates. Okay, technically we have to do two things. We have to choose coordinates, and we also have to choose something called a metric, all right, which is a way to measure distance. Okay, the way that we think about measuring distance is normally handled by some type of idea known as an inner product. Okay, you all are probably more familiar with calling this a dot product, which is the version of this that we use for Rn. Okay, that's how we choose to measure distance. And then we, of course, discussed the idea of coordinates, and we tie the idea of direction to our coordinate system. So with those two things, then we can start talking about representations of the direction and magnitude of a vector. Okay, and when we write down our coordinates, then that gives us the ability to extract both of those pieces of information. The length of a vector is the square root of the dot product of a vector's coordinate representation with itself, right? And the coordinates themselves are having to do with the choice of our basis. Okay. This thing here is a transition matrix. Okay, and it is how we move from one coordinate system to another. All right. And we will next time pick up some more details of this, do a few examples, talk about how coordinate systems work, and also draw some parallels between how we do things when we're talking about vectors in Rn, but also the other types of vector spaces that we have discussed, because all of these ideas also work in those contexts. All right, enjoy your day, everybody. I'll see you next time.